Welcome everyone, my name is Ádám Vécsi, and I am going to present you formal language identity-based cryptography, which is a joint work with Attila Pethő. Identity-based cryptography is an essential branch of the public key cryptography, which was coined by Adi Shamir in the 80s. Originally, he was able to build a signature protocol that was based on factorization, which was too slow for practical use. The breakthrough came with the Bonner-Franklin identity-based encryption protocol, which was based on pairing, and it managed to provide feasible performance for practical use. The uniqueness of identity-based cryptography lies in the fact that a public key is a string that identifies an entity in a particular domain. One may think about an email address, a username, or phone number. This is in direct connection with the core idea of identity-based cryptography, which was to simplify the certificate management and eliminate the need for certification authorities. In the public key infrastructure scenario, public keys and user identities are bound together with certificates. With identity-based cryptography, however, there is no need for such certificates, since public key corresponds directly to user identity. Furthermore, the public key may contain more information than just the identity of the user. This extension of the public key with domain-specific data enables a wide spectrum of advanced use cases. Although one limitation of identity-based cryptography is that the public key of the receiver must be bit accurate to the encryption key to be able to extract the belonging private key. Consequently, identity-based cryptography is not able to handle finely granulated access policies. One step towards key flexibility was fuzzy identity-based encryption. The main novelty was that it handled public keys as sets of attributes, not as strings. With this concept, it could add the fuzziness into the scheme in a way that only a certain amount of overlap was required between the encryptor key and the public key of the decryptor, not a total bit accuracy. The advantage of this system was much faster group encryption, but it comes with runtime drawbacks in every other function, called by name setup, extract, and decrypt. Multiple schemes are focusing on a similar area of identity-based cryptography. One notable is the identity-based encryption with wildcards. In this solution, the encryptor key is a pattern, which is treated as a vector of bit strings and wildcards, as you can see in the presentation. Here the wildcards are representing any kind of bit strings, so the example pattern represents that anyone who has an email address which looks like something at cs.something.edu can decrypt the encrypted document. This protocol allows us to use a super flexible encryptor key, but if too much wildcard is added, it slows down excessively. The concept of fuzzy identity-based encryption, that the public keys are sets of attributes, started a new branch called attribute-based cryptography. This branch follows the same idea, but with an extension that they are building an access tree to keys. In the leaf elements, there are the attributes, and the other nodes are logical gates of AND and OR operations. There are two main types of attribute-based cryptography. One is key policy, and the other is ciphertext policy. The difference is that which data is associated with policies and which with sets of descriptive attributes. The key policy is working with ciphertext associated with sets of attributes, and the user public key with policies, while the ciphertext policy is the opposite. There are also more advanced attribute-based cryptography schemes, which allow more flexible access trees with the occurrence of negation or multi-use of attributes, as you can see in the examples. These extensions make attribute-based cryptography more and more practical. However, a significant drawback of the attribute-based cryptography schemes is that they require more computation on the user-side functions, namely encryption and decryption, with the growth of the complexity of the SS policy. This directly affects the usability of this protocol, since several potential applications target devices with limited computational power. Tomida Kawahara and Nishimaki were able to create a scheme that managed to fix this issue, but only for the decryption, and only if the SS tree is built with AND and OR gates and doesn't contain multi-use or negation of the same attribute. If it is a step further, but it involves less SS policy flexibility. Our solution is called formal language identity-based cryptography. We built an encryption scheme, and with minor changes we managed to create a digital signature scheme too. They are very similar, so I'm going to present only the encryption scheme now. I will introduce the definitions of the components at the appearance of the protocol. With that being said, let's start with a definition of the public keys in our protocol. The domain in which our system works defines a set of possible attributes of entities. An attribute is a pair where the first element is the name of the attribute and the second is a formal language, which is the language of the possible values. An example of an attribute is the next pair. The name, let's be the eye color, and the formal language of possible values is the animation blue, brown, and green. Of course, these attributes are defined by the domain itself, so there is no need to give these by hand. These attributes give the structure of an entity, and the properties are defining the actual instances. As you can see in the definition, the property holds the actual values of an entity. Finally, we came to the definition of the public key of entities in our protocol, which is a set of properties, including a subset, which is the unique identifier of the entity. The identifier is required because we built our protocol as an extension of the identity-based cryptography system. Similarly to those systems, ours is working with a trusted third party called private key generator, which generates the requested private keys from the master secret. The protocol itself starts with an initialization function called setup. This function generates the public parameters of the identity-based cryptography system and the master secret. The next step gives the essence of the protocol. Before the encryption, it is required to obtain an authorization formula. It is a logic formula that contains Boolean operations and attribute constraints. The attribute constraints defines which are the required values for a given attribute. So with the authorization formula, the sender defines which entities are authorized to access the decryption key for the encrypted document. As you can see in the example, there is an authorization formula containing two attribute constraints with an AND operation. The first constraint is given with a regular expression and means an email address ending with @company.com is required. The second is given with an enumeration, and it gives what job is required of the entity. After the formula is created, the sender creates a digital signature to it with an identity-based signature protocol. It is required to prevent the forge of the authorization formula. In our protocol, the public keys of the receivers are only used for authorization. The encryption is done with a generated key, which is the sender's public key expanded with a unique generated property. This is in direct connection with the authorization formula. If the formula didn't change, there is no need to generate a new key. It is reusable, but if the formula changed, it is required to generate a new key. Also, since it is an expansion of the sender's public key, which was used for the digital signature generation for the formula, this guarantees that the formula and the signatures are not fake. All the extra steps are done from the sender side. The next is the encryption of the document, which is done with an identity-based encryption protocol. The receiver tries to extract the decryption key for the given generated encryption key from the private key generator. The private key generator checks if the signature of the formula is correct, then starts an evaluation process, which is the examination of the receiver's public key if it fits the authorization formula or not. If everything was okay, the receiver can perform the decryption. As a summary, we could say that the protocol extends existing asymmetric cryptography protocols with the idea of the authorization formula and the shared generated encryption key. More advanced example of the authorization formula can be seen in this tree diagram. Imagine that there is a need to encrypt some data which is shared between multiple hospitals with different access policies. With formal language identity-based encryption, all it takes is to create a finely granulated authorization formula. The SYN formula means that people with med.unidep.hu or medical.mail.hu email address and with one or more medical qualifying examinations are authorized to extract the decryption key to the encrypted data. Furthermore, if someone has an xhospital.hu email address and all the given other properties next to it, as well as one or more medical qualifying examinations, he is authorized too. As you can see, the formula can be more and less complex based on the requirements. The advantages of the protocol are that it provides a flexible target definition, as it was shown in the last example. Also, the authorization formula doesn't require to target any specified entities, only properties. So it supports future entities who might not be suitable right now, but later some properties of the entity change so it fits the formula. If a student finishes medical school and passes the medical qualifying examination, etc., he could decrypt the data. The most important advantage is that the runtime of the client-side functions is not dependent on the complexity of the formula, which is the main issue of the attribute-based cryptography. There are two disadvantages of the current system. One is that the authorization formula always travels with the ciphertext, so it might pump up the cipher size if the formula gets more and more complex and big. The other disadvantage is that the runtime of the extract function, which is a server-side function, depends on the complexity of the authorization formula because it includes the evaluation of a public key fits the formula or not. Well, as we have arrived at the end of the presentation, I would like to thank for the financial supporters of the research and also to the audience for the attention. Thank you.